Hi guys, good morning. Last last lesson, I know you didn't get the handouts. I've checked. There's some logistic issue happened because the administration sent the handouts to a teacher who is away, so they can't print the handout. So I hope this time you guys have already got the handouts. If you haven't, please let the teacher know. They should know where the handouts are now. And the handouts is about the forces. And so because you didn't have the handouts, so I need to repeat a little bit up from last lesson. It's just like you can just treat this like a recall. And we start with the nature of forces. We understand forces is required to change the state of motion of the objects. So that means you need force to make things not just move but actually accelerate. And and each force you need certain agent to apply the force, and there must be another agent who experience the force. Okay, and force is a vector. That means you need to consider the magnitude and as well as the direction of a force. The unit of force is Newton, and force can be measured by spring balance. So if any time you want me, so you can't want me to stop. Sorry. Uh, Anytime you want to copy something, you just raise your hand, ask a teacher to slow down or to pause it, so you can copy it. Thank you. And we've learned two common types of forces. One is tension. Tension is a force which exists on taut strings, stretched strings, rubber band, or springs. All the tension must be in pair, and also they must act along the length of the string, pulling the objects at both ends together. And that figure actually show you why there must be two tensions, because when you pull the object, not just the object is feeling the tension you're acting on it, but yourself also yourself is also experiencing a backward tension on yourself. So that's why there are always two tensions and along the two objects. But these two tensions they are from different objects and on different agents as well. For example, the tension on the load is from the man, is acting on the load. Okay, and when we last time I mentioned about how can you draw tension on certain figures. Those arrows just refer to tensions. Then the next force is friction. Friction is a force that will appears when there's a relative motion, or if there's no relative motion but there's a tendency of relative motion between two surfaces in contact, then there will be frictions. And of course, here you have to understand what to mean by relative motion. That means the two surfaces must move relative to each other. What does it mean? It must have different velocity. For example, if they have the same velocity, and so you know they don't have relative motion. Uh, then it's about those force diagrams. How can you draw friction on the object? So it's to oppose the relative motion. So in some cases, it's easier to see. For an object sliding towards the right, then friction would be to the left. When it's sliding down and inclined, the friction would be up along the slope. But sometimes it's less obvious. For example, when you're walking, your body is moving forward. Does it mean the friction should be backward? No, the friction is in the same direction or as your movement. Actually, the friction is helping you to move forward. Why? Because while your body is moving forward, your body is not in contact with the ground, but your feet are, and your feet are actually slipping backward, so the friction will be forward. That's why we say friction is helping you. So when we talk about friction is to oppose the motion which is not entirely right, you have to be very precise in that description in physics. You must know that that actually means friction opposed the relative motion, not just motion, between the two surfaces in contact. That's the way we understand the nature of opposing motion in physics. And this example is actually quite good. You see both the horse and also the block is pulling is towards the right, but then they have very different friction on them. For the block is sliding on the ground, so the friction is to the left, but for the horse is running. Okay, so when it's running, the horse legs should be moving backward, and so the friction um, on the horse is actually to the right. So the friction is helping the horse to run, but it's opposing the block to moving and to move, opposing the block to move to the right. All right, and here are some common things about friction you can look. All right, so if you think you need more time to copy the things from the previous video, you can ask teacher to pause the video or reverse back for you to copy them. If not, I'm going to continue. Today we are going to finish off the handouts. There are two more forces, and then I'm going to talk about a combination of all the four types of forces we've learned. The third type of force is called weight. Weight, another name for weight is gravitational pull or gravitational force. So when you see the word gravitational, it comes from the word gravity. So you understand the gravity. Gravity means something. Actually, in physics, it's not something. It's a field which drag things towards each other. And the gravity comes from Earth for us because the Earth is the largest massive body in our proximity, right? It's of course another one is the moon and the sun, but they are rather further away from us. So for us, we are under the influence of the gravity of the Earth. So that's why when we are talking about the gravitational pull on the Earth's surface, or the weights, it refers to the effects from the Earth rather than from other astronomical bodies. Okay, what are the properties of the so-called weight? The Earth and other heavenly bodies pulls every object around it. The attractive force is always attractive, so that's the first property. It's called the weight. And of course, the weight here is a bit different to a daily use of weights. That actually means how heavy we are, but the weight here is a force. The weight of an object points towards the center of the Earth. Okay, so if you can observe the Earth from a distance, then you can and you can draw the weights caused by the Earth. For example, there are objects like those black dots there, and these arrows are the weights of those small dots. Small dots. That means objects with masses. All right. So if you can see Earth from that distance, you can see all the weights are towards the center of the Earth. That's why we can say weights of the object points towards the center of the Earth. But that's less relevant to our daily life, because normally we won't observe the Earth from that kind of distance. We're on the Earth. So the more common thing is like when we are very close to the Earth, then the weight of the objects points vertically downwards. So that would be in this case. So you draw your so the weight, and this weight is perpendicular to the ground, perpendicular to the horizontal level. So that's why it's vertically downwards. That's how can we draw the weights. And of course, you might think about how can we draw a weight of a human body, for example, right? So before I'm talking about human body, how about how can I draw a weight of a block sitting on the ground? Strictly speaking, you can't draw the weight at any point. So for example, if you try to draw a weight here, it's not right, it's not correct, strictly speaking, okay? And so the proper way to draw the weights is always near the center of the object. Okay, so here's the weights. So how about human being? So like, okay, if we draw a human body here, okay, playing the film, playing the film, like many of you are doing. Not you're not here. I trust you're not playing your phone. Okay, I mean sometimes you do it during the break, of course. You are good students. And okay, so how can we draw the weight of the objects for human being? It should be near the chest, here. Here's the center, because that's our center of mass. Okay, and these points you can call them as center of gravity or center of mass, and here's the center of gravity of a human being. For a human being, the center of gravity is close to our chest. All right. Okay, and then we are going to talk about a very important equation about weights. How can we find the weights? Weights equals mass times g. Mass times g. We all know g means what? G means acceleration due to gravity. And And we have a value for G. So G normally just means 9.81 meters per square second. So the weight can be found by using that formula. So if you know your mass and the mass times your G would be around your weight. Okay. And that weight, again, and I need to say that again, it's not the weights you get when you are standing on a balance, because that would actually, that's mass. So sorry for the confusion. So when you're weighing the so-called weights in our daily life, that actually means mass. All right. So for example, if you are standing on a balance, trying to see have you lost some weight. Okay, so you saw there's a reading here. Okay, and the reading in what kind of units would that to be the reading? So normally it's either in pounds or kilogram. Nowadays in Australia, I think should be in kilogram, right? So let's say you see your weight as how about 50 kilogram? All right, so that's the so-called weight in your daily life, but it's not actually the weight in physics. It's the mass in physics. So it's mass equals 50 kilogram. Okay. Okay, so let's say this is Victor. All right. So how can we find the weight of Victor? Then you have to use weight equals m times g. So use 50 times 9.81. And what value you will get? All right. So sometimes you can do some very quick math by just assuming 9.81 is just around 10, then you have 500 Newton. But let's try to do it more precisely. So that becomes, okay, so next time when someone asks you your weight, okay, so for example, someone asks, Victor, what's your weight? And Victor can say, my weight is 490.5 Newton, and that's quite scary because normally when you are talking about weights, they assume you are talking about in kilogram, but in physics it's in Newton, and they might not know what Newton is, so it's kind of funny thing to do. Right, just a bit confusion between the daily language and also the physics, but I really like it because, to learn physics is to make you become very kind of nerd. That means sometimes we kind of communicate certain language other people don't understand. All right, so let's move on. And what's the relationship between mass and weights? Here is a very good a very good example to talk about this. If you just simply take an object to the moon or another planet, which quantity will be changed? Mass or weight? Okay, remember this. Mass will never change, but weight will. So mass is a constant. Weight is not a constant. Weight depends on two things. Weight depends on mass and g. But mass is a constant. It never changes. G is not a constant. It depends on the planet. Which planet you're on. Okay, the planet. There may have, oh yeah, yeah, that's good. All right, so on the Earth, that 9 is 9.81. Do you know what would be the value? So that's on the Earth. That's on the Earth. What would be the value on the Moon? Do you know that? On the Moon? Anyone knows? You can check, but you can't use your phone, so you can't Google. Sorry, I need to do that for you. So it's around 1/6 times of the value on the Earth. So you just divide that number by 6 is around 1.6 on the Earth. So for example, if Victor travels to the Moon, then his mass will still be 50 kilogram, but his weight will become much smaller. His weight will become how much? 50 times 1.6. 50 times 1.6 just 80 Newton. So it is much smaller than his weight on the Earth. All right. So here's the relationship. Weight depends on the planet and the mass. Mass is a constant. All right. So let's say an object weighs 60 Newton on the Earth and 10 Newton on the Moon. So it's 1/6 times, Which of the following statements are correct? First, the mass of the object on the Earth is around 60 kilogram. Is that true? Let's calculate the mass of the object on the Earth. Yeah. So we use this one. So on the Earth is, 6 Newton on the Earth. 6 Newton mass we don't know, but on the Earth we know G should be 9.1. So if you use your calculator, yes, it's really around that number. So it's 6.1 something. So it's around 6 kilograms, fair enough. But second, the mass of the Moon is 1 kilogram. Is that correct? I give you some time to think. You can discuss. Of course, I can't hear you discussing, but I guess that there might be some argument there. I guess Nana should have the correct answer. Our friend from the German. All right, so the mass of the object is around 1 kilogram, which is wrong because the mass should be a constant anywhere in the universe, not just on the Earth or on the Moon, but it's in the universe. Every corner of the universe, the mass should be the same. All right, that's it. The acceleration due to gravity is 1/6. That's already done. I have told you. Okay, then it comes to last type of force, which is called normal reaction. All right, normal reaction. So what do you mean by normal reaction? All right, so I will just draw a picture for you. So if you, let's say, if someone looking at their phone, okay, like this. All right, so of course we know there's weight at his chest, which is W. So that's a downward force pulling this guy towards the Earth. But what's the problem? Why he's not falling down? For example, if he let go his phone, okay. For example, if he let go his phone, and the phone is here, it's not the same phone. It's much bigger. Anyway, So if he lets go his foam is dropping. And again, there's another weight, that different weight, there's another weight of the foam, another pulling force on the foam. Sorry, it's too small. I need to. Okay, all right. I hope that's fine. So why the foam will be pulled down um, by the gravitational pull or the weights, but not the human being. The human being, I mean, this man is still standing on the ground without falling towards it. Why? So the difference is that W is the only force acting on the foam, and that force is a downward force. But for that man, W is just one of the forces. There are other forces acting on the man which stop the man falling like the foam. What's the force? So that's the force we need to introduce. So you feel the force when you stand on the ground for a very long time. You feel what kind of feeling? What kind of feeling here? I hope my drawing is good. Oh, really hate this. This I don't really like. Oh, anyway, what's the feeling here when you stand on the ground for such a long time? You feel kinds of soreness of the muscle, especially from your feet. Okay, and that kind of feeling is from a force called normal reaction force. Let me draw you the normal reaction force. These are the so-called R. We use R to to represent the normal reaction force. And this type of forces occurs when an object, just like your feet, is in contact with a surface like the ground, the surface of the ground, and also you are pressed, okay, presses against it. For example, one of your feet stands on the ground, so you are in contact with the ground, and also that um, that foot is pressing against it. So that's why there is a normal reaction. Okay, that's the how can we get normal reaction? You need to be in contact, and you need to press against it. Do you think you are on your body right now? Do you think there's any normal reaction on you? Of course, because you are in contact with the ground and should be in contact with your chair, right? All those surfaces you are pressing against them, so they will give you normal reaction on different parts of your body. And all the normal reaction must be perpendicular to the ground. It must be perpendicular to the surface. Actually, that the word normal here again is a scientific term. It's not the idea we normally learns in normally. Okay, it's not the normal we use in our daily language. All right. So it's like in math or in physics, that normal means being perpendicular. Remember this. That's why it's called normal reaction. Okay. The next question is about to indicate direction of normal reaction acting on the objects. Of course, the block is sitting on the ground and pressing against the surface. So here's the normal reaction. Remember, you need to make sure they're perpendicular. The other one need to be perpendicular. Perpendicular means make sure they form a right angle here. Do we have normal reaction here? Yes. Here. Here's the corner pressing against the ground here. So that's normal reaction. Just one normal reaction? No. How about here? Another normal reaction here. How many normal reactions here? Think about this. I give you possibly 1 minute to draw it. All right. So think about this. Can you draw it? Excuse me. Okay, so if you need more time, ask the teacher to pause the video for you. I just don't want to make my video file too big. I will write this normal reaction here. So that's one. And that's another one. Remember, when you are drawing normal reaction on a circular object, all the normal on the circle must be towards center. It's a mathematical fact. It's a mathematical fact, especially if you are learning method or specialist math. Remember this. All the normals will be towards the center of the circles. Just to know, I'll be off here, right? Oh, it's terrible. Not a good drawing here. Oh, what happens? Yeah, be better here. I use the same letter R, but actually they should be different. So you can say it's R1, R2, R3, R4. So just for this one, R1 and R2. Good. Right. So here are all the normal reactions. So next, we are going to learn free body diagrams. What do you mean by free body? Free body is, again, the sense free here is very is restricted to the context. It just means you single out one body to consider. You single out the body. You don't need to draw all the forces in that for all the objects, but you just draw all the forces on a particular object you choose. So that's why it's called free body diagram. Okay, so remember it's all the forces acting on an object, a particular object, and normally there would be four major forces you need to consider. Of course, they are not all the forces in the universe. There are plenty of forces, and we haven't included them. For example, magnetic force, electrical force, applied force by your hand on something. All right, and there are plenty of forces, but for mechanics, we consider these four forces first. All right, don't just look at the picture, look at the description. So object placed on horizontal table. Okay, horizontal table. is placed on it, so it's not moving. Think about the four forces. Weights is about the gravitational pull. So weights should always there. Always there. It must be in a certain kind of gravitational field. Okay. And for most of the situation, weights just means the gravitational pull from the Earth. Our normal reaction, remember, you need to have surfaces. You need to press the two surfaces pressing each other. Friction, remember the key word is relative motion. You need to see the relative motion. And tension, you need to see what? You need to see something taut. String, taut, string, spring, stretched or pulled, rope, things like this. Okay, so here, weights must be here. So let me draw W first. And here it must be normal version. For normal version, try to draw it from the context, from the context between the two surfaces. Right, an object pulled across a rough horizontal table, so it's rough. So it's pulled across, so it's moving, let's say. And it must have weights. It always have its weights. Because of the weights it's pressing against the surface, so then you have normal reaction. But apart from all those forces, you need to consider it's moving on the surface. So that's a relative motion between the block and also that horizontal surface. So draw the friction here. The friction must be drawn on the object, not on the surface, but on the object, because the force is acting on the object. Ceiling, so a object hung from a ceiling. It's always here. It's always here. Weights. Do we have normal reaction this time? No, there's no surface for the block to press against. And how about other forces? Friction, any relative motion, any tendency of relative motion? No. But there's a stretched string, a string under stretched, so under pulling. So is a tension here. So normally you can draw two tension, but the other one is not necessary because that tension is on the ceiling. You don't need to draw that because we are drawing free body diagram. For free body diagram, it's always about the body you choose. And all right, the last one is a block placed on a smooth incline. So smooth incline. Weights. All right, be careful. Weights must be vertically downward towards the surface of the earth, not the surface of incline. Some people might make mistake like drawing things like this, and this is wrong. It must be like that. Okay, so I will get you some time because this one is the one we are using in our assignments, right? So please, can you try to draw it? Can you try to draw the other forces? You can think of one. Yeah, I'm going to count for 10 seconds. Okay, so if you need more time, just ask a teacher to post a video for you to have more discussion. If not, just one force. Some of you might have drawn that fraction. Some of you might have this one, but it's not true. There's no such fraction because the incline is smooth. For smooth surface, there's no friction, no tension as well, okay? Draw free-body diagram for the objects. So black dots represent the center of gravity. So this time it doesn't talk about what forces you need to indicate. So you need to think about if there are extra forces you need to consider. A luggage dragged across the ground. The first force you would like to include must be always the weights. The second force is your normal reaction here. Any other force? So we see some bearing here for the luggage. If the bearing is still okay, is still functional, then it should be rotating. Okay, so let's say if that's the so what should I do it? It's very difficult to draw. So if it's moving forward, then the bearing should roll like this. So at that point, the bearings are actually rolling, moving to the left. At that point, I mean, because it's rolling like that. So the friction should be, because you are moving to the left, so friction actually becomes forward. So I should draw a forward friction here. Okay, should there be any other force way? So we've got R, weight, friction, but you can imagine, so how can this luggage be dragged? So there must be someone here, must be someone like, okay, someone, okay, so it's not a very good habit, right? But actually I saw someone doing this, okay. And okay, so if someone is pulling his luggage, walking like this, and it's not recommended, okay? Some accidents bound to happen. All right, so and there must be another force acting on that bar he's dragging. So and we would say that's a tension here. That's a tension here. Yep. And that's it. A block moving upwards and in along a rough inclined plane. Okay, I will get you some time to try to draw the forces on the question 2 and question 3, and I need to drink some water. So I pause the video. So can I get you 5 minutes? Try to finish those forces. You can discuss among yourself if you're not sure about certain things. And okay, please pause the video for 5 minutes. All right. Weight and normal reaction. and rod free incline, there must be friction. So it's moving upwards, but it doesn't say whether it's pulled upward or dragged upwards. It just says moving upwards. It could be like you project it initially, but it's in the midway of its journey going up. So that means it doesn't require an upward force along the whole path, right? Good. And for that one, a bob swinging down, weight, no normal reaction, but that's tension. Any other forces? Mm, you might add, if you want, a little bit air resistance here, but normally you can ignore that. That's the only force you might consider adding to the diagram. That's it. If you don't want that air resistance, that's completely fine. Normally, we don't need to consider that. It's too small. All right, so let's think about how can we add forces. Let me ask you one question. All right. So let's say, how can we revert that? Sorry. Okay, so let's say Ben suffers a punch uh, by who? By Taylor, possibly. Okay, with a okay a 3 Newton punch and 4 Newton punch by Leonard. All right. What is the total forces? That's total, okay. Um, punching Ben. All right. So here's a question. So it looks very similar. So if you ask any non-physics people, they would say 7. But if you say 7, it's just for physics. For physicists, it's just one of the correct answers. That's it. It's not actually what we are going to use just for 7 Newton. So I'm going back to this question. You can have all sorts of thinking now, but I'm going back to this example to answer. Okay, what would be the total force? I don't think I should say what is. Sorry, my English is not good. I should say what would be. Would be. That means there are more possible answers. Okay, so I give you some example first. For example, if there are 2 Newton and 3 Newton acting on a block, what would be the resultant force? That should be 5 Newton. Why? Because both 2 Newton and 3 Newton, they're acting on the same direction, so you add them up. Okay, so it's 5 Newton. If that 2 Newton, 3 Newton, one is to the left, the other to the right, what will be the resultant force? So the resultant force is the combined effect acting on the object. So you can't say that 5 Newton, can you? Because that two forces are obviously are in opposite directions. So you can say, oh, there are 5 Newton towards the right or left, both are wrong. It should be just 1 Newton towards the right. Why? Because 2 Newton to the left cancel out 2 Newton to the right, so there should be 1 Newton remains to the right. It's more complicated. We are not going to learn it right now. So, but I just show you a little bit. So because we are going to learn it next year, and that helps to answer how much force bands suffer from the punch. Um, Parallelogram method. How can we add two forces like that? If you have two forces not parallel, not like the forces we've just seen. They are either in same direction or opposite. How about they are perpendicular? You can still add the forces. You can add them like a parallelogram. You draw like so you can say this rectangle, but actually rectangle is one type of parallelogram in a broader sense. I just draw. It's a bit off, I know. All right, so that would be our resultant force. And the other way is tail to head method. I'm not going to do that now. So how can you find that normal reaction force? You can say, okay, I can use F1 square plus F2 square. All right. That because they obviously you can use Pythagoras theorem. But how about other forces like this one, F1, F2? Okay, you can still do it. You can still draw a parallelogram, and the resultant force is just diagonal. But in this case, you can't use that Pythagoras rule anymore. So you can see to add two forces together, there are many ways, many possible answers. It can be just add two numbers together. The two numbers might be one take away each other, and it could be like that one. It could be you use Pythagoras, or there's no mathematical rule for that one. Actually, there is, but you haven't learned it. So let's go back to the question here. Total force punching. Okay, so you can say one possible answer is for, of course, if Lena and Taylor they try to punch Ben from the same direction, and you can just add their forces up. But if Lena punched Ben from the left, and Taylor do that from the left, and they will cancel out a little bit. So the resultant could be just 1 Newton. And the other way can do it is like a Taylor tries to punch the band from the left and Leonard from the front. In that case, two forces are perpendicular, and the total force band experience would be like a 3 square plus 4 square, which is 5 Newton. And for there are infinite many possibility. And in the end, I would like to tell you that any value is any value between 1 Newton and 7 Newton. Any value is possible. So that means the minimum force that's Ben in the end can receive is 1 Newton, and maximum is 7, but any value from 1 and 7 is possible, right? That's it. And you know how can we add the two forces like that? Or you need to so that the key point is forces are vectors. So when you are considering the combined force, the resultant force, you need to draw the picture to see how can we add them up or do them. Sometimes you need to do the takeaway. Okay, so All right, for example, when I give you 4 forces, a ball has 4 forces acting on it: 15 Newton left, 100 Newton right, 30 Newton left, 6 Newton right. Construct free body diagram, find the resultant force. Okay, and all you need to do is draw a ball, and you need to draw a diagram, okay? And 50 Newton on the left, 100 Newton to the right, 30 Newton to the left, 6 Newton to the right. All right, so the resultant, obviously, you need to add the forces to the right, take away the forces on to the left. So it just become 80 Newton and to the right. Oh, good. Oh, good. So easy. You need to do that as homework. And do we have anything else? Not much. And you can try to do some of the questions here. Answer is in OneNote. Okay, I hope this lesson is better than the last one. You've got your handouts and you got everything filled in. All right, so I will see you next week. I hope I've then by then I am COVID free. All right. So see you next time. Bye.